I wanted to record myself uh, implementing a new type of GEMM algorithm or GEMM All-Scatter algorithm. So currently we have the regular All-Scatter, which is a fused version, which is you do some level of GEMM and then you do the remote rank transfer, so iris.store. It's pretty simple because it's all of this code is for the actual gem code, like for the actual gem kernel, up to this point, and then the for loop around the remote rank and this iris store is the only thing that was needed to enable like a fused all scatter implementation. I then copy pasted this code to write the workgroup specialized version, which essentially says that for some program IDs, or here it means workgroups, I'm going to be doing gem, and for the other ones, for the remaining ones on the GPU, or the ones that get scheduled later on, I'm going to be doing com. And in the gem part, I'll do the store, and then I'll unlock a lock, and then in the com part, I will be spinning on that lock, waiting for it to be unlocked. Once it's unlocked, I will do the iris.put from this store in the local space, which is current rank, to all the remote ranks, and it's a loop over it. So pretty simple, actually, not a lot of changes to get this working as well. And similarly, what I want to do is copy that folder, paste it, and then I would like to implement a new pattern, which is going to be what do I want to name it? It's GEMM All-Scatter Producer Consumer, I guess. The names are kind of getting really long, but we'll go with that. Okay, so the producer, yeah, we'll name it producer, and then we'll write another kernel that's the consumer. So this is going to be the gem. I'll actually rename it afterwards, but for now that works. Let's rename this right now. What? Okay. Okay, perfect. I kind of wanted to record myself and time myself and see how long it takes. So I'm starting actually doing this implementation about 3 minutes into the recording. Okay, so the concept is pretty simple. What we're gonna do is launch two kernels instead of one. One will be doing gem, and then the other one will be doing um, the all scatter, and they will be on separate streams, so they will both launch at the same time, and yeah, they'll both launch at the same time, and then one will be just spinning, waiting for work to be created, and the other one will be the one producing the work and unlocking the lock. So very similar logic, but instead of having it in this if else, um, we will instead write it as a separate kernel. So let's start. So I'm just gonna copy the whole signature because it kind of makes things easier. Oh, I changed the wrong function here, so I'm gonna close that just so I don't make changes to that one. Don't need that if else statement thing in there. we might use this timing stuff, might be relevant. We don't need the bias, so we probably need numxcds. Probably don't need GMSMs. Do we need GMSMs? All right, we'll worry about that later. We don't need block K because we'll only be working on M and N dimension. The stride can stay as is. Don't necessarily need all these local strides. Might come handy, but we'll just add them back if we need them. Don't need the bias pointer. Don't need ABC. We just need the... Actually, do we need C? So does C get used? Trying to think. So I actually don't even need C in this kernel, so I might have to go back and clean up this old kernel. So don't need C. I'm just gonna change C global to C. It's nicer to read. And then I will call it persistent all scatter. And then I will call the, oh, this is useful. I will call this, I don't know if it's showing up in the video, but I will call this persistent gem. Okay, and I can get rid of this if statement 2. It's not a work specialization anymore. Tab this back. So it's easier because I'm building it off of another kernel, but there's not going to be a lot of changes required to do new kernels either, especially because Triton has so many cool examples already that people can work off of. Okay, total tile. So I'll just copy paste this computation because it seems important. Yeah. Okay, so copy paste that computation from the other kernel. So what this is saying is I'm gonna get the program ID, which is the workgroup ID in Triton. There's some num XCDs for AMD GPUs. We have these accelerator dies, and the L2 is on each of these like accelerator chiplet. So to make sure everything nicely ends up on the L2, we actually need to do a little bit of computation. Basically grouping together tiles in single work groups. So this computation is essentially doing that. I'm not sure if this will need to be changed for this to work better, but for now we can just leave it as this. It doesn't really matter as long as we're getting bijective PID out. So num PID M and just number of tiles in M and N dimension. Total number of tiles will be multiplying them together. Each one is calculated by taking the M dimension and doing a sealed division over the tile size. Com SMs. Yeah, I guess this is where we could potentially use the GEMM SMs. What will be total num SMs divided by com SMs. Or we could just make it. Yeah, I'm just gonna use com SMs for here. Com SMs. Don't need the concept of GEMM SMs or num SMs in there. So okay, so for PID it starts at 0. For all tiles I need to do this. Enter this loop, figure out some swizzling thing that's okay. It's just boilerplate code. Potentially can find a way to get rid of it, but it's a L2 swizzle kind of thing, creating space filling curves in the L2. Then I begin working on figuring out where my output is, calculate the various mass, calculate the global offset, and then what I want to do is spin on the lock for that given tile, and then once that tile is ready, I will take it, load it from, essentially take this put means that copy whatever is in this location in your current rank, which is like your local pointer, into a remote pointer. So that's all it's doing. So actually that's all I need to implement persistent all-scatter. This will slightly change if it was bulk synchronous, which we will do next. But for now we can like leave it like this. I'm gonna change this to com SMs too. I don't know if that's relevant, but we'll figure this out later. Going all the way at the top, I think we can get rid of the concept of num SMs, just rely on gem SMs. We do our gem, great. We do the store, make sure we have the correct cache modifier so it writes all the way through to global memory. Have some sync barrier, debug barrier. You might not need this, but that's okay. And then do a store on your locks to make sure we unlock the lock after writing the C matrix. Okay. I believe that's all we need. We can clean up some of the C bit later because I think it's it's thinking, so it thinks I'm using it because I'm accessing the type, but I could very much easily do that for the with the other stuff. I don't need a local C and a global C. I just need one C in all scatter example. Yeah. Okay. Cool. So that's basically done. Persistent gem is done, and um, persistent all scatter is done. So now we go to the wrapper code, which is actually calling this stuff. GEMM All-Scatter, then change the name so we can desert consumer, so we can import the correct thing. Import persistent gem and persistent all-scatter. So persistent gem kernel, and then I will set the, so maybe I'll call, yeah, maybe I'll leave this simple and just do persistent gem here, and then I'll call the alt scatter kernel outside. I don't really need to, yeah, I don't necessarily need to call it here. It'll make it simpler if I just did it here. Yeah, I might just do it here. I will lose a little bit of tooling support. No, I changed my mind. No, we'll do it outside. It's a bit easier and a bit nicer if you do it outside in the benchmark. So what I mean by that is, so I have this mapmel wrapper. All that's calling is that gem function we wrote. So it's going to call that gem function. We can get rid of numSMs. We don't need that. I don't know what else we remove from there, but we'll probably run into that run into that later. NumSMs can go away. And then in the benchmark, we have mapmel wrapper, and then from gem we import persistent all scatter. And then I'm gonna use the same benchmarking setup. There's not a lot changed here. I'll just change com SMs, number of SMs for all scatter kernel. Okay. So in this case, we can specify like the two separately. Ideally, you'd want, since it's persistent kernel, you'd want to occupy the entire device and partition it so that the total of these two equal to the number of SMs. Okay. This looks good. The type setup looks good. Everything else basically stays the same. I just want to see what I was passing in for C matrix. So I can do that cleanup as we go. Did I miss it? Where is it? Oh, local C and global C. So A, B. I don't think I need this local C. I just need C. Don't necessarily need the other one. Oh. Yeah, looks a lot cleaner now. And then with GemStream, we can launch this. And then what I'm gonna do is I will say this is range pop for gem. Yeah, so I will put this here. So in this case, kernel timing, I'm gonna create a new kernel timing. Let's say communication. This is what I meant. It's gonna be easier if I put it outside. SMs. There is no num-sm, so we gotta change that. Get rid of it from here. Matmul doesn't need it. So communication will have its own like timer thing. So matmul, and then here I'm gonna set up the communication stuff. So oh, I don't want to type that again. Communication, and then arguments. I think it's setting C locks mn. Okay, so let's see. So it's C locks and then mnn. I will figure out what they are in a second. And then stride cn cm stride bias. I could probably get rid of this. And then block size, group size, G size, block size remains the same. It's COM-SMs. Okay, probably you have to put a little, make it a little bit verbose. I might actually create a matmul, like a wrapper like matmul for COM, so I don't have to do this setup on here. Decisions. So this is basically like cleanup code. It doesn't have to do anything with the implementation. I'm just kind of trying to also clean up as we go, which is probably not a good idea, but it's fine. So for actually launching the kernel, you can see it's pretty simple. You specify the kernel name, specify how many like work groups you want to launch it with. So in this case, it should be actually what is it? GEMM SMs. Yeah, good catch. As I was explaining it. So benchmark. So I'll just do a copy paste this here. Probably should set it somewhere. Nah, let's see what happens. I'm gonna pass it in. Let's see if it's gonna complain. Yeah. That's actually all we need, I think, to launch the kernel. So now you can go to it, C locks mn. So we need mn, which is just like you can get it from the tensor shape. So basically like this. So we can just set it to so now that I think about it, am I sending the full n or the local n? I think I'm sending the local n. So, okay, let's see. Because it's split, and that's the bn. Yeah. Okay, cool. So this is kind of what I think we need. So some locks, which is already allocated, and I'll show that in a second. Oh, we also need the stride. So the stride is just these variables. So after n, I can do the strides. We see, and then block sizes COM-SMs, num-XCDs. So block sizes, yeah, there you go. We don't need K block size, we need G size. Block size, G size M, which is group size M, right here. COM-SMs and num-XCDs. COM-SMs and num-XCDs. For num-XCDs, what do I pass? It's 8, but like I gotta okay. We'll just use this logic here too. Let us put that logic maybe here. Stream equals torch.CUDA.stream. Forgot about that. So yeah, actually I'm just gonna put 8 here. It's probably a really terrible idea, but for now it's fine. Heap basis, current rank, world size. So that would be world size, heap basis, current rank. Current rank is just like shmem dot something rank. Oh, it's being passed in. What is it passed in? It is passed in, so this rank variable. So what was it? Heap basis, current rank, and then world size. Heap basis, current rank, world size, and then the timing stuff. Yeah. This should be everything we need. And then what we're gonna do is make sure that the kernel timing is properly being reported. Okay, yeah. We'll probably have to like output that to somewhere. Yeah, we'll probably have to output that somewhere too. So reset it. C validate gem, which was just gonna do some validation for us. Everything else roughly stays the same. Add the basically wherever this loop exists, we have to add the communication times. And I have to figure out how the final time is being reported. Validate ms. I guess the do bench thing reports it. Yeah, iris do bench Triton ms. Perfect. Cool. So that's being reported as total milliseconds and being used for calculation. So I will just use this here. Did I get rid of C properly? No, I did not. So I think I can actually remove. I don't think I need these strides. So I'll comment them out because I might need them and I'll have to uncomment them. But for now we can do this. So is the global used somewhere besides that? Oh, actually I'll use these and comment these out. Yeah, I think that's it. Okay, if it fails, we'll know. In the actual code, there's C strides. Okay, perfect. And now in the gem, in the actual kernel, just make sure we comment out. Yeah, I should probably just use C. I like C better instead of. I know global and local makes it nice, like makes it more readable, but so this is gonna be CM and this is gonna be CN. This is gonna be C, and then in here we get C. Sure, we can just leave that as is. Okay, so now that we have, let's recap our setup. So I'm like 25 minutes in, which is freaking amazing. Out of which I was like cleaning, most of the time I was cleaning up the code, or cleaning up a little bit. So we have a GEMM kernel that's producing the tiles, and as it produces tiles, it stores them through the caches and unlocks a lock, which is this locks array on tile ID. The persistent kernel takes in that lock array, takes in the C. So one result is already ready in the local GPU. It will spin on that lock for every tile. So this is the spin lock, and then once the tile is ready, it's going to scatter the results, which is really, really easy implementation. And this is just the launch code. We are basically launching a gem kernel. And then this is the scatter code, which once launched, once launched, it's gonna launch it on two separate streams, gem stream and com stream, at the same time. So this is launching the matmul call, and this is the actual persistent kernel for all-scatter. Cool. I think it's working. I think that's how I intended to write it. So let's test it. So on the right side, I already have a Docker setup. And in this Docker setup, I can specify. Actually, let's pick better defaults for. So calculator 256 minus. Okay, we will assign 48 SMs to com and 256 to gem. And then we have to be in the right file or folder. So this is 11th example. Okay, let's see what fails. So now that should be it. This is a very large tensor. It's 16K by 16K by 16K. Okay, something failed. Oh, arch isn't defined. Right, I forgot. I can make arch like, oh, it's so annoying. Okay, I can make arch potentially a input parameter, but for now we'll just do that. Anything else is broken? I don't see any other complaints. Okay, while that's running, I'm gonna look at some other stuff. Okay, I kind of got distracted, so let's see what's wrong. Oh, both events must be recorded before calculating time. Oh, did I forget to time it somewhere? Kernel time. Oh, I think I have to do end time. Yeah. So this probably this part. Yeah. And then I'll also add, while I'm here, I'm gonna also add a NVTX marker. So later we can profile it. And the barrier. Do I need this barrier here? Yeah, I guess. Okay, I can just leave that. Okay, so I forget. That records it, that adds it. Okay, I think it's good. I should probably pick a smaller size so I can actually iterate on it faster. Right now it's allocating a 16K by 16K by 16K tensor, which is going to be huge. This is what happens when you do too many things at once. Okay, so it says in this argument, input position 1 must be a tensor, not compiled kernel. Trace, not compiled kernel, trace back. So it's angry about what I send in here, which is C, and what I allocated. Oh, okay, I forget what that was, so I'll have to look at another piece of code. So in another example, I just use global C. C. Oh, my bad. Yeah, I actually don't need to set it to anything. It's actually, this is so stupid. So C, it's assigning this kernel to something, and that kernel is becoming an object that I can use. But all I needed to do is just call it, I'll call it SS for scatter kernel. Yeah, that's ugly. I'll just leave it as this. Okay, let's run it again. Ooh, first try. It passed. So this is the output that this benchmark script produces. You can edit it however you like. There's a lot of customizations that you can do with it. But in this case, what's cool is that it ran the benchmark. It tells you that the small MNK was this, so you can see the end dimension was being partitioned. The results are valid, so it passed the validation completed since we gave it that flag. So success equals true. Total milliseconds was this. GEMM milliseconds was this. GEMM number of experiments, basically number of times it ran and averaged over, and the COM SMs was this. So the total SM will include the time of this and this, which is great. And you can mess around with it more, like you can change the block size and a bunch of different things to like see if it works. So I think I'm gonna change just a few more things and then end this video here. So we have effectively implemented a, yeah, there's some things that could be nicer, but that's okay. It's a future problem. We have effectively implemented a GEMM plus all scatter in a producer consumer kind of way, where we are asynchronously launching two kernels, and they're each producing their output, and yeah, and it's working with very little code changes to the existing all scatter example. So just want to make sure the comments are correct. Yeah, that's correct. Yeah, everything looks good. So I'm just gonna stop the video here. Thanks for watching.